Hey, welcome back to Math with Patrick. Today is July 4th, and we're solving problem number 185 from the Daily Epsilon calendar. And we need to do some tiling today. So we have a rectangle, and it's tiled by squares with distinct side lengths. How many neighbors does the smallest square have? So we're tiling rectangles, and I'm not sure what the rectangle is going to look like. Maybe it is almost a square. Actually, rectangles could also be squares, so maybe it is a square. Or maybe it's going to be really long too. And so whenever I'm dealing with these problems with like a lot of variability and what I'm working with, I do like to think of the extremes. And so this is technically a rectangle because I forget if the definition, no, yeah, the definition of the rectangle is we have two pairs of sides that are congruent and we have four 90-degree angles and all the sides are straight. But then it's totally fine if these are also equal to each other, right? Because every square is also a rectangle, but every rectangle is not necessarily a square. Anyways, so we're dealing with rectangles. It might be a square too, and we're tiling it. When you tile something, it just means to cover the whole thing with shapes, essentially. So here I just tiled this rectangle with four probably other rectangles, sorry, 8 other rectangles. I could tile this guy with some triangles, maybe it could look like that. And it just kind of depends what shape you want. Some really famous tiling techniques are tessellations, where you have some kind of wacky, wonky shape, but then somehow it's able to kind of copy itself throughout the whole plane and cover the plane perfectly, even though it's an unfamiliar kind of shape. Here, though, we are tiling our rectangles, or maybe this square, with squares with distinct side lengths. So, like for example, with this long rectangle, maybe I could just split it up into like 8 squares, and let's just pretend that this is like 8 times the length of this for now. I did tile it, but then these squares that I tiled it with don't have distinct side lengths. In fact, they're all the same. So this isn't going to be like a valid tiling here. And apparently, once we find this tiling, the smallest square is going to have a certain amount of neighbors, and apparently there's 4 neighbors. So like maybe I'll have, well, I guess it would make sense that if we had like a small square in the middle, then I could have one square here that kind of looks like a rectangle, but bear with me, and then like another square here, another here, and then like another there. So I guess it would make sense that a square could have 4 neighbors, because the instant that I like try to put a fifth one in here, I guess I could do that, huh? Right? Like maybe we could kind of put an extra square somewhere in there. So 4 makes sense, but 4 isn't the obvious only answer. Maybe we could even have 5 or more. I don't really know. Oh, well, actually, hold on. If we do assume that this is the smallest square, we're not going to be able to put a smaller one on it, because then we would have a new smallest square. So if we happen to tile the rectangle with distinct side lengths, all other squares must have side lengths that are larger than this guy. And then, so we might have one of those scenarios where our side lengths kind of have this spiraling pattern where we just kind of like go outwards from it. And then clearly, oops, that's more rectangular than I wanted. Clearly, we could have 4 squares kind of surrounding the small guy. I'm wondering what happens if we try to like put a square that's a little bit offset from that one. And honestly, at this point, I'm just going to erase that bounding rectangle. That's a little silly. So if I do have a square that's offset, well, I could kind of put another square right here. So let's try it out. I could still put another square here. And I'm trying to like make them have distinct side lengths. So that's why they're getting bigger and bigger. Ooh, but then see, look, if I try making another square here and the side length must be longer than the small one, now I'm leaving a gap right there. And this gap, if I fill it in with a square, is going to be a smaller square than there is before. Wow. So actually, we don't even need to find a tiling for the rectangle. There could be any of them, but it's just that if we have a smallest square in the middle, the only logical surrounding squares are going to be squares that have lengths that are longer, and thus those lengths have to start at the vertices or the corners of our original small square. So I guess it's just 1, 2, 3, 4. And yeah, sure, I don't have a rectangle to tile, but the small guy must have only 4 neighbors. So just to make sure, I wrote it all out. So here's the small square, I just called it S. And here's the idea where we could place 4 different larger neighbors around S, and they're all going to share one vertex with S. So this larger square right here shares one vertex and it doesn't share the other, because that one is shared with that square. And this vertex is shared with that square. And this vertex is shared with that one. So we do have an example that has 4 neighbors. And here I'm just kind of disproving or I'm proving that any other scenarios couldn't happen. Because if we tried placing like smaller squares around S, then S would no longer be the smallest one. So we can't have any scenarios that look like this, where we have smaller squares around it. Also, we can't have squares that are the same size or that share 2 vertices, because then we don't have non-distinct squares. And also, S is no longer unique. That's the same thing. S is no longer the smallest, is what I meant to say, because now we have 2 squares that are tied for smallest. So S is no longer the smallest, and we don't have distinct squares. So there can't be any squares that share 2 vertices with S. So they must share at least or just 1 or maybe 0. But then if we do try to have 2 squares that share no vertices like these 2 up top, then we run into an issue where as we tile other squares around S, like this one and this one, once we've done that, then we have this kind of weird gap underneath. And here we're either forced to create squares that are smaller than S or the exact same size as S. And we already covered that we can't do that. So this is really our only scenario where our smallest square has 4 neighbors kind of fanning out. And let's see if I can tile this rectangle with different size squares. Well, at least, actually, no, I don't think I can. Not off the top of my head. I saw this example online, and I will kind of continue with what I saw, but then you'll probably realize why this doesn't work, for this problem at least. Because what I saw was a 6 by 6 square, and then a 5 by 5 square. Then there was a 4 by 4 square right in here. And then finally a 3 by 3 square. 1, 2, 3, kind of like this. And then it does create a 1 by 1 square right here. And then here's our smallest square. It has 4 neighbors, different sizes. But then, of course, I didn't tile the whole rectangle. And I don't think that I could use different sized squares now because, here I might have to be stuck with another 4, I think. And then here I'd probably be stuck with another 5. How would this go? Maybe something like this, right? So here's another 1 by 1, here's another 5 by 5, and here's another 6 by 6. And so here I tiled this rectangle, but I did use copies of my other squares, so sorry about that. It didn't actually really tile the rectangle as I should have in this problem. I reused squares of different sizes, but hopefully this is kind of a good enough example to show that in a kind of real example, our smallest square is surrounded by exactly 4 neighbors. Ooh, so I found a really useful website. This is called squaring.net. And well, it's useful for today's problem where someone out there has, or maybe many people out there, I'm not quite sure, have found basically all of these perfect squared rectangles, as in they are rectangles and we put squares in it. So here you can see that 18 plus 14 makes 32. And then if you did 14 plus 10 plus 9, you get 33. So this is a 33 by 32 rectangle that has been tiled with squares. And they're all distinct, they're all different sizes. And of course, we can zoom in on our smallest guy, and we can see that it has 1, 2, 3, 4 neighbors. And even if you zoom in on smaller squares, maybe not the smallest, you'll also notice that they kind of have that fanning out idea going around the smaller kinds of squares. So this is, I believe, the smallest squared rectangle, in that there are 9 squares in here, and that's like somehow the minimum number. You can't make a squared rectangle out of 8 squares for some reason. Here's another example with 9 squares in it. And so this one has the smallest square of 2, actually. And then it has 1, 2, 3, 4 neighbors. So we could do like higher order squared rectangles, the order being like how many squares tile that rectangle. And so here are some, maybe those ones aren't drawn. Oh, what if I do this? I have just been poking around this website. I'm not really sure how it works. It looks like we can draw any of these order 17 squared rectangles. Yeah, and there's 17 different rectangles in here. And 17 different squares in here that tile up the whole rectangle. And our smallest square looks like this 4 right here. And then we have 4 neighbors around it. Interestingly, we also have 4 neighbors around the 5, 4 neighbors around the 7. So that seems pretty typical of smaller squares in these diagrams, that we're always going to have 4 neighbors. So this again is squaring.net. Maybe you can poke around here yourself. It's kind of fun to see all these diagrams. But hopefully that satisfies your curiosity about what these diagrams look like when they're actually drawn correctly. Anyways, answers 4. I'll see you tomorrow. Bye.